Well, how are you doing, Mr. Sams?
Oh, you're back to the accent this time?
I got accent because I'm a smart guy.
Accent.
Hello, how do you do?
Howdy.
How come you not try new accent? You tried last time.
I did. I don't know. It might come back later.
Might come back later?
We'll see what
Okay.
happens.
Guess what to talk about today?
More thermodynamics?
And it's like what's the big word? It's that dirty word, right?
Math?
Math.
Oh, yeah. Last
We
time was
must-
conceptual.
Now we
This
have
time we're going
lots
to
of
do
math.
the math.
So what do you think our kids need today when they're going to be watching the podcast?
Calculator.
Gotta have the calculator.
Yeah.
Probably you're also going to need, ladies and gentlemen, your book.
Your book.
Your book, and in the back of your book, you will find. Oh, where's our book? Here it is, right here, Mr. James.
You got it. Okay.
We're good. Turn to the back of your book, and you'll find the section on thermodynamics.
It's in the appendix.
Everybody say thermo.
Dynamics.
Dynamics. Oh, and we've got even an audience. Want to say it again? Audience.
Thermodynamics.
Say these people are amazing. So,
Right.
we're going to be doing a lot of math today. So, let me talk a little bit through this. When we talk about calculating thermodynamic quantities, I want to do a little review with you. In chapters 5 and 6, actually chapter 6, we had a conversation about how you can calculate delta H. Now, what is delta H again?
That's their enthalpy.
Now, what's that mean? That's a fancy word.
Yeah, it's the measure of heat change.
So the heat change in a reaction. We learned in that particular chapter there are 4 ways to calculate delta H.
Yep.
The first one was calorimetry. And you might recall that was like Q equals MC delta T, and then you divide by the moles.
Yep.
All right. And the second method was Hess's Law version 1, where we added a bunch of reactions. Okay, so think back to how you did that, guys. All right. Go watch podcast 6 point whatever to figure that out. You remember the third one was?
Hess's Law version number 2, products minus reactants.
Yep, that's Hess's Law version 2.
Yep, and the products minus reactants, the values for that are going to be in the appendix in the back of the book, the one that I was just looking up a second ago.
So products minus reactants. And the fourth one is bond energy. And guess what? We're not even going to talk about that until we learned about bonding. So that's chapter 8. So
Later.
And it sounds weird, chapter 8, we're in chapter 16. Remember, we don't do it in standard order.
We go out of order.
We're out of
special
order.
like that.
We're special. So that's kind of what we're going to do. And that's just a review of something we've learned before.
Yep.
All right. But there's also 2 other thermodynamic quantities.
Right. We learned last time we have delta S, which is
called
entropy.
That's right.
That's the change in the amount of disorder in a system.
Okay. Disorder. It's disorder like your desk. It's
like
a very disordered
It's like you
thing.
order food and then you disorder it because you decided you didn't want the cheeseburger.
What's also
No?
true, if you think about it, if you eat the food, it
Oh, yeah,
becomes
then it gets very
organized,
disordered,
and it gets
yeah.
disorganized in your stomach.
It does.
And then it becomes all into your body,
The
and it's
rest
very
of the
disordered. Yeah.
stuff.
All right. Now, something very important about delta S. The units must always be what?
Let's see. Usually given in joules
Per
Kelvin. Yeah, and you have to convert those to kilojoules because delta H and delta G usually show up as kilojoules.
Yeah, delta H is kilojoules per mole, and delta G is kilojoules per mole. And for whatever reason, all the thermodynamic books, in fact, if you have your book open to page A21, which has the table of thermodynamic quantities, you will discover that they are in joules per Kelvin right here. And so you want to watch that.
Yep.
All right. Okay, so now let's talk some more. Now, delta G, how do you calculate delta G? That's a
Delta
funny
G.
thing.
Well, last time we learned delta G equals delta H minus T delta S.
All right, that's this first one. The most common, I say by far the most common of all the equations.
Yep. Now, you're going to learn a new one when we talk about electrochemistry. That's a funny looking E.
Yeah,
It looks like the euro. Is that the euro symbol? I think that's for euros. But
Yeah,
anyhow,
it's supposed to be an
NFE.
E0.
It's like a big capital squiggly
we'll learn
cursive
what the
E.
heck, what in the world is an E? It has to do with voltages.
Yeah,
and
that's
stuff like that.
electrochem.
And so that's chapter 17.
Yep,
And
then
so
we're gonna
ignore that for right now.
We're going to tie delta G into equilibrium. Like
Ooh.
we said last time, you're not done with equilibrium because that's how chemistry works.
There's the big K.
We talked briefly about this last time, but we have delta G equals negative RT times the natural log of K.
All right, so now we
we'll
want to
come
do a
back.
reaction.
Yep.
So we want to find delta G, delta H, and delta S for this reaction. And we need to go to the appendices in the back of the book. So if you have not done this, pause the video. Go to that page, page A21. Now, if you are watching this on the internet, you need to get a textbook. And it is always in the back of the book, the table of thermodynamic quantities. And then you can look up these values.
Yep.
Okay?
And if you have Zumdahl 6th edition, it's in A21.
Yep, that's right. So we have a reaction here.
Yep.
And let me copy it down.
Yeah, we
It's
have
2
2SO2.
S. Oh, I guess I probably should not
Use the
have
right end of the pen.
eraser turned on. I have the eraser turned on. So 2SO2. That was my
And that's a
problem.
gas.
Hey, that's a funny SO2, huh? I had the other feature
The shape
turned
feature
on.
turned on. We have too many things turned on. Plus
O2
gas.
makes
It's a gas, by the way.
two
All these are gases.
SO3s. It's not important. Now, what I want you to do
Not
is
for
I
this
want you to look up delta H and delta S
Oh, yeah.
in the table.
I got to get to my sulfur section here. So,
So-
most of these are organized by element. Okay, here we go. So we want delta H for SO2.
Yeah.
All right, delta H for SO2 is negative 297.
Negative 297.
And that's
okay?
kilojoules per mole,
Yeah.
if we care.
Kilojoules per mole right here. Okay.
Okay.
What's the oxygen? Actually, oxygen. Mr.
Oxygen,
Sams,
yeah.
what is oxygen?
Well, that's not in my book. I can't find it.
You know you can't. Actually, it is in your book. But
It
you
is in
know,
my
if you
book,
looked
you're
it up in your book, you know what you'd find?
0.
It'd be 0 because remember, elements in their standard state. This is a gas. This is a gas. Will be 0.
Yeah.
Okay. And then the sulfur trioxide.
SO3 gas, negative 396. By the way, and Mr. Bergman said that the states don't matter. In this problem, they don't matter because these are always gases. But sometimes, be careful. If it says water gas or water liquid, they're going to have different values for delta H.
Okay.
So be
Now
careful.
delta S. Now, actually, it's actually S0, not delta S, isn't it?
Right. And H0 too.
Actually, yeah, it's all right. So I'm erasing that. All right. Now, actually, an important point: the oxygen is not 0. I think it's 204. You do which one are you doing?
SO2 is SO2 is
SO2
248,
248.
and that's joules per kmol. Don't forget.
Okay.
And then oxygen, we actually can look that one up because S is different. It's
205.
205.
I was
Yeah.
pretty close. I thought it was 204.
Yep.
All right. And SO3?
SO3 is 257.
257. All right. So we want to do products minus reactants.
Mm-hmm.
All right. So if I do the sum of the products, so the products for the SO3, I'll take 2 times negative 396 minus the quantity of 2 times negative 297. I could ignore the oxygen because, of course, it's 0, right?
Yep.
And that comes out to be...
Just about done. Negative 198 kilojoules per mole.
My pen is doing a little dragging thing here. I don't know what's going on.
Don't know. Finger on the button.
No, I don't think so. Okay. And
All
now
right.
for the S, so this is delta H. So for delta S, I'm going to take, what, 2 times 257
257.
plus
Nope.
0. Oops.
Oh, yeah.
I guess there's no something there.
Wait,
My
what?
mistake. Minus the quantity of 2
Two times 248.
248 plus, is there one oxygen? I think there
There's
is.
just one oxygen, yeah.
Plus
So plus 205.
205, close parentheses, and that comes out to be...
Hang on, I made a mistake. I have to go back.
You're going from 2 to...
Oh, he's going
3
to try to do it in his head, folks.
It would be about
Can he
positive
do it?
100.
Parentheses, negative 187.
Negative 187. Oh, it should be negative. I should say negative
Yeah.
100. Okay, my mistake. Negative 187. Now that's joules,
Joules
per
per
Kelvin
kmol.
mole. Okay, now how do we find delta G?
Well, we could do it 2 different ways. We could also do products minus reactants, but I think it's easier just to use the delta G equals delta H minus T delta S.
Now, in our book, it says that the temperature is 295, I think. So we need to use a temperature. So we have to have a
yeah.
specific temperature. And I think
That's
actually,
not printed in your paper, but
we'll actually print it for them
yes.
when it comes out.
Yeah, we'll fix that.
That's something we will fix.
So
So,
let's-
delta H is what? Negative 198.
Yep.
So this is negative 198. Now watch what I do this, folks. Minus the Kelvin temperature, we said 298, times delta S. Now what am I going to put in for delta S, though?
You're not going to put 187 because that's joules, so you need to multiply that. No, divide that by 1,000 to get.
So I did this in
kilojoules.
my head. Now some of you may need to do this. I took this, of course, took this number, negative 187, and I divided by 1,000 to convert it to kilojoules. And so, folks, you've got to watch that. This is in joules. It's in joules, and this one is in kilojoules. And you must have them in same unit or you have problems, right?
There's the accent.
Okay, it's very
back.
problematic. Okay.
All right, we got negative 254 kilojoules per mole.
Now, what does that mean?
That means for every mole, we're going to release 254 kilojoules of energy. So that's energy that's going out of the system, so it's available to do work.
Now, another thing I want you to realize, folks, it's very important to understand the sign of this. This is negative, and so if it's negative, what does that mean about delta G?
Delta G is spontaneous.
So that means it will happen by itself.
Yes.
And while we're at it, delta H is negative, so that means it is exothermic. Everybody say exothermic. So it's exothermic. That means energy is released. And it's negative here, so it's getting more
ordered.
So or less
delta H
disordered.
and delta S are working against each other, but that's okay.
And I would have predicted that this was getting more ordered because of the reaction itself.
Right, we've got 3 moles of gas becoming 2 moles of gas.
If you look up here, you've got 3 moles of gas being converted to 2 moles of gas. So 2 moles of gas are more ordered than 3
Right,
moles
because
of gas.
gas is messy.
Yeah.
Chaos.
There you go. Okay, guys, this next one is we're going to try and solve for K. Remember, we learned that there were a couple of ways to solve for delta G, 3 ways, delta H minus T delta S. And then we're going to use the equation delta G equals negative RT.
Negative RT ln K.
Natural log of K. And so we're going to use that equation to solve this problem. So, in this particular problem, we know that delta G is what?
Negative 33.3 kilojoules per mole.
Negative 33.3 kilojoules per mole. That looks like a circle, doesn't it, instead of a triangle?
Okay. Your shape thing turned back
I think I must have turned it back on. Okay, so now what you're going to do is that delta G, now here's something important, is negative 33 kilojoules per mole.
Right.
Now we've got to convert that to joules per
right.
mole. There's 1 kilojoule is 1,000 joules. Now you'll see why I need to do that. I could do that without a calculator.
Yep.
That will be negative 33,000.
It's actually 33.3.
Oh,
so you need like
33,300 joules per mole. Now, why do I do that? Because if you recall R, that's the gas law constant, is 8.3145 joules per Kelvin mole. So I must have like units. I could have converted R into kilojoules. I just find that a little bit cumbersome. So negative 33,300 is equal to negative, because it's negative RT, 8.3145. I won't put the units on here. And the temperature at this, I didn't see
25 Celsius,
so that's
it says.
298 Kelvin, right? Just add 273 to that, times the natural log of K. Okay, now, what you would need to do mathematically, this could be done with a solver, but I think we're going to teach you how to do it without a solver.
Yeah, just do it with the math.
So we're going to divide both sides by negative 8.3145 and 298, right?
Yep.
So negative 8.3145 and 298. Of course, they cancel on this side. And what do you get, Mr. Sanders,
You
you
get
divide these numbers?
13.4.
13.4. The negative signs, negative divided by negative gives you positive,
Yep.
is equal to the natural log of K. Now, how do you find K in this particular equation? You'll take
the inverse of natural log, which most calculators hit the second button, then you hit the ln button, and it's the little e function.
So e to the log of something is the something. In this case, e to the log of K is K.
Right.
So I'm going to take e to the 13.4 power. And you get?
686,780. We'll do 686,780.
780. Now, sig fig wise, what have we got here?
It's like 3 sig figs.
I think we're going to go with 3 sig digs there. So that'll be 68,700.
Yep.
So 68,700.
Nope. Sorry. 687,000. 687,000.
Oh, I didn't do that right.
Yeah. Sorry. I told you wrong too.
687,000.
Yep.
There we go. So 687,000. Now that's a K.
And equilibrium Ks do not have units. We don't worry about
no
them.
units on that, right? Now that's a big number, Mr. Simmons.
That's a huge number.
So when you have an equilibrium constant that's very big, what does that mean?
It means it favors the product side extremely.
Remember equilibrium shifting to the right.
Yes.
And I would have actually predicted that this would have a very high equilibrium constant. Why? Because I had a delta G which was negative.
Spontaneous.
And whenever you have a negative delta G, you will have a very high value of K.
Yeah, because it's...
Or at least a positive K.
Yeah. Yeah.
Or a number bigger than 1, I should
And
say.
it makes sense because the spontaneous reaction is going to favor the products.
And so that's how we do this. All right, now we're back to the PowerPoint. Let's jump now here. Calculate the value of delta G for the following reaction at 390 Ka, where et cetera, et cetera, et cetera. So here's the problem. So how are we going to tackle this one, Mr.
Well, we've got some concentrations here, and we want to find delta G. So if I know concentrations,
you can find.
We should be able to find K, products over reactants.
Yeah, so we're in this problem.
Are we assuming
folks,
we're at equilibrium here?
Yeah.
I think we kind of have to, otherwise we're going to do
we
Q.
have to be at equilibrium, so we'll add that to the paper, I think.
Yep.
Okay. So what we've got is the reaction is into, this is the classic reaction, plus 3H2 makes 2NH3. And it's at equilibrium, so we have 2 molar ammonia, so this is 2 molar. And the hydrogen is 1.25 molar. And the ammonia, no, the nitrogen,
3.01.
3.01. So the equilibrium constant, the K expression, would be the concentration of the ammonia.
Squared.
Why do you need to square it?
Because the 2 coefficient.
Yes. This is a K. Remember how we did Ks? Let's like Kc from chapter 3 over the concentration of the nitrogen.
Chapter 3?
Chapter 3. Chapter 13.
There we go.
I knew. I was just checking on you. Make sure you got the answer. And then you'd cube that right there.
Yep.
So now we actually just plug in some numbers. In H3 is 2.0, and we're going to square that. I know that's 4. If you 2 squared is 4, divided by 3.01.
That was kind of fun.
Times 1.25, and then you cube it. And Mr. Sams is Mr. Calculator boy.
Mr. Sams just made a mistake again.
And he has to do it again because he's slow on calculator. He must make a mistake all time.
Syntax error.
Syntax error? I thought you were smart.
I left out a parenthesis. No.
4 over 3.
This is not my day. There we go. 0.68.
0.68. All right, so that's K, folks.
That's K.
And our equation was delta G equals negative nRT, natural log of K. So,
nRT?
not nRT, negative RT. I was thinking PV equals nRT, and I was getting very crazy on myself.
All together.
And of course, R is 8.3145. What was our temperature? 298?
Temperature
389.
389 in this one.
All right. 389 times the natural log of 0.68.
Yep.
And when you get your calculator
you
out,
get 1202.
1202. And the units on that does have units. That'll be kilojoules per mole. Now, it's positive,
It is
right?
positive.
Even with the negative sign here, right?
Yep.
So that means that this one would not be spontaneous.
And that makes sense because it's a small case. K is less than 1, so it's going to favor the reactant side.
Makes sense. I want you to add this somewhere. This is really the delta G equation. Delta G, hello, what happened there? Let me redo that. Delta G equals delta G naught plus RT, natural log of K. Now, what's true when delta G equals 0, Mr. Sams?
Delta G equals 0, we're at equilibrium.
So when you're at equilibrium, actually this should be Q.
Q.
I'm going to get my things right here. Actually, let me erase so it's easier to see. We've got this cool erase feature right now. We like this. Okay, if that's equal to 0, then you'd say delta G naught plus RT, natural log of K, because now you are at equilibrium.
Right.
So if you resolve this equation, delta G naught is equal to negative RT, natural log of K. So that's where that equation comes from that is important. There's this important equation, but this is the equation that it comes from.
Yeah.
And then, of course, while we're at it, delta G is also delta H minus T delta S, right?
And we can find it with products minus reactants.
Also, you can say delta G, is the sum of the products from the back of your book, PROD, minus the sum of the reactants, etc. So we just want to make sure, actually, while we're at it, there's delta G equals negative NF E naught. And that's, we're going to learn about that one. This is in chapter 17, which is actually our next chapter.
So I love electrochemistry.
I do too, because electrochemistry is so cool because you can make batteries. And we can talk about how my dad's propeller in his boat corroded because he did not have a sacrificial anode.
Oh, sacrificial anodes.
The old sacrificial anode problem.
Yeah.
Yeah. Well, I hope you are learning much in your science land so that you can be a happy chemistry person. Hello, my name is Bill. I don't know. Bill!
Oh no, Mr. Bill.
Mr. Bill. Yes, I was thinking of Mr. Bill.
You guys are way too young to know Mr. Bill.
You should do a Google search
That's Saturday
on
Night
Mr.
Live from the
Bill.
80s.
From the 80s when Mr. Bergman was a younger lad. And you weren't even thought of, probably.
I was
Okay.
probably in middle school.
You were in middle school in the 80s?
Yeah.
I was in college. 82 to 86.
Oh, 82.
college.
I was only 5 years old in 82.
Oh, you are so young. 82, I go college. College boy in 1982. Yes, indeed.
Yeah.
Oregon State University. What college did you go, Mr.
I went
Sam?
to Biola University.
Biola. That's a little private one, isn't it?
It is. Middle
Yeah.
school.
Now, don't get that confused with, like, Ohio State. I went to Oregon State, the Beavs. Okay. Well, we hope you guys are having a grand time. And now you know which colleges we went to. How's that
Yeah.
for fun? We'll talk to you later. Bye.
Bye.